dele, o professor Andrés Anabalón, na Universidade de Concepción, no Chile. Então, só para comunicar quem está seguindo o seminário do professor, esse seminário está sendo dado dentro de uma aula de um curso que nós temos às quartas-feiras, às 4 horas. Esse curso é online, né? Então, hoje nós estamos usando o horário do curso para ter o seminário do Andrés. O Andrés é uma pessoa que é realmente um especialista na área de ADS, CFT, uma pessoa bem reconhecida internacionalmente pelos trabalhos que faz. Eu acho que essa semana você vai ir para Turim. Sim. Ele vai dar um mini curso lá na Universidade de Turim, na Itália, e o ano que vem vai estar passando, eu acho que um ano no IFT, sim, aí em São Paulo. E aí a gente está pensando, se o CBPF existir no ano que vem, né, com a falta de dinheiro que há, mas se o CBPF tiver alguma verba, a gente vai convidar o Andrés para passar uma semana aqui, 10 dias. Ele gosta muito do Rio de Janeiro, adora o Rio de Janeiro. Todo mundo gosta. Então a gente vai convidar para ver se dá um mini curso aqui para nós no ano que vem. Eu vou tentar fazer uma ponte com o pessoal da UFRJ também, que tem o Nelson, o Henrique Rossi, que trabalha com a ADS também. Então, muito obrigado, Andrés, por estar conosco aqui e compartilhar o meu conhecimento aí conosco. Obrigado.
Muito obrigado, Jota, pela coincidência engraçada. Lá tem o Alfonso Balón Bayona. Anabalón, Balón Bayona.
Obrigado, Andrés.
So I will do the lecture in English because.
Okay, in English because maybe some people abroad.
Well, and also my Portuguese is not so good. I can go to a restaurant.
You survive.
Yeah, I can survive. I cannot speak these things are too technical. Well, thank you very much for coming to my lecture. I love Rio de Janeiro. I think it's one of the most beautiful cities in the world. Actually, the first time I came to Rio, I looked around and said, this is so beautiful. Why not everybody lives here? But then you live here and you understand that it's another problem.
Don't say that in São Paulo.
It's amazing, you know, like, well. So, well, I will tell you something that probably you already have heard a lot, and that is this duality between QFT and general relativity, okay? But like, the thing is like, okay, this is kind of old now, right? It's like 30 years old. So we already kind of understand it relatively well, much more better than 20 years ago, I would say. So one can actually make this connection very precise. So I want to do like a very precise calculation first to show how to connect general relativity with quantum field theory. And it's an amazing calculation because it's very easy and it's very good, very nice. And this calculation will allow me to introduce what I have done later, right? That is a continuation of this story, of course. So this is like, what I will do is that I will compute the energy of a certain state in the QFT, and I will do the same calculation using general relativity, essentially. And I will get a very close result, and I will discuss this, okay? So, in holography, what you do is, well, it's something that is very amazing, that is like, of course, you start with the reality, right? The reality is this, that we live in this background, right? So I said, nobody disagrees with that, right? So we live in a background that is very close to that, right? So, and then, like, of course, all the QFTs that are realistic are defined on that background, and all the problems that people have are in that background. So, like, what the idea is that, okay, so this is our background, we will not change that, but we will add something else. So we will say that this background is actually part of another space that is this guy. Okay? So this is AES, right? This is AES 5. And the idea is that your QFT lives here. But when you have a QFT plus an RG flow, that the flow is the radial direction, right? So this is the same. So what is magical is that you can describe this geometrically, right? So you can describe geometrically the existence of a QFT plus an RG flow, and the master theory with the master variables to describe this is general relativity. In general, it's general relativity. So GR plus fields. In B equal 5 describes a quantum field theory in B equal 5. Okay? So this is like, this is the general idea of holography. Right? So what you want to do now is like, let's check this. Let's see how it goes. So the first thing that one wants to be kind of like be more precise about this, and one way of being more precise is like asking yourself, for instance, how the Hilbert space of the QFT is related with what I say in gravity, right? So I have a Hilbert space here, and I have gravity here. So how these things are connected, right? How the Hilbert space is connected with what I will say in gravity, right? So the Hilbert space in the QFT, they say the Hilbert space is related with the boundary conditions that you put in this space. So the Hilbert space of the QFT is related with the boundary conditions in the space where the QFT is. This is what defines the Hilbert space. So this is related with boundary conditions. So to test this, so for instance, and something that is actually very, very phenomenologically relevant because it's related with what people do in the lattice, is that we can think like there are some fields that are periodic in one direction, right? When you have the lattice QCD, you take a direction that is periodic where the fields are periodic, right? Or anti-periodic even. They call it twisted fields, okay? When they are anti-periodic, they are twisted. So let's play with that idea. So let's modify our background a little bit. So now there is a direction that is compact, okay? So this is a circle with radius d. So this 5 takes values between 0 and okay? And this is nothing to do with gravity, right? This is just a QFT. And then in this background, I can consider, this is like in this book, there is this book of QFT and pure spacetimes. It is very famous.
Viral Davis.
Viral Davis. So in Viral Davis, you can go and see this calculation, okay? Viral Davis. So in Viral Davis, you can go and see, for instance, you have a scalar field, phi, capital phi. And you can see, you can quantize the scalar field in this part. And you can either impose periodic boundary conditions or anti-periodic boundary conditions on the S1. So this is the twisted field, and this is the normal. And you go and you compute the expectation value of your Hamiltonian in this thing. It's a very straightforward calculation. You do like the expansion mode, and in the expansion mode, you just take the ones that are periodic or the anti-periodics, and this give a different result. Okay? You need to do regularization, but it's nothing complicated. Well, so you give that expectation value of the energy is for a scalar field. You get this result. So is minus pi over pi 2, 6 delta Q, C, and B2 X. Where B2 is the volume of the Y set. Right? You have always this infinite volume. See, so the density of energy is well defined, but the energy is multiplied by the volume, which is infinite. X is a number that comes from the Riemann zeta regularization of the calculation. That is has this value, so it's set. So with 1 and infinity of 2n cubed is equal to 8 divided by 120. So this is 8 times the Riemann zeta function of minus 3. And this is for period. So this is for periodic. And if infinity to n minus 1 cube, and in this case you get a negative number. And this is anti. Okay. And this is the result. So now there is something interesting here. Already you can make an observation that is like in a theory that has the same number of. So this is, and actually you can go and do the calculation for every other field, and at the end, the only difference is that you get here the number of degrees of freedom. So you just have to multiply this for the number of degrees of freedom. So if you do this for the vector, for the say the gauge field, the photon, you just get 2 times this. Okay? And there is so.
But for the fermions, do you impose anti-periodic boundary conditions?
Yeah. So the things like you have both choices. In this case, you have both choices. So you can even for the fermions, you can put periodic or anti-periodic, because in this case you have 2 spin structures. So you can put either periodic or anti-periodic. It's the same. So the thing, what happens here is that, like, you already can see that. Well, the only difference is that these numbers are interchanged for the fermions. So for the periodic fermion you get this, and for the anti-periodic fermion you get this. So they are not really the same. Okay. So, so it's like, so the thing is like, if you put,
Andres, okay, if you have the photon, you just put the number of degrees of freedom. Sure. And if you have an abelian, let's say a sort of
this is a free field calculation.
Okay.
So this is free field. This is the free field limit.
No self-interest.
This is the kinetic field.
Okay.
Okay. So I will do the non-abelian. I will do the other calculation, but I have to do this calculation. So this is free field.
Okay.
Thank you, but this is a good point. Free field. So this is a free field. And okay, so let's do that now. Let's do this free field calculation for supergeometries. Okay, in the sense that we just need the matter content. So like supergeometries is a theory It has 6 scalars. Okay. One 6 scalar degrees of freedom. 2 vector degrees of freedom because there is a jamming field. And there is 8. There are 4 byte fermions, so there is 8, let's say, fermions. Okay? So this is supergenius.
But supergenius useless matter or just pure gauge?
Supergenius is the Lagrangian is minus f squared.
Yeah.
Minus sine bar.
Yes, plus the 14, no?
Yeah, minus the phi squared minus a potential for phi. And this is this. So n equals 4 supergenius.
N equals 4. That's not my point.
Yeah. N equals 4.
Okay.
So the one, so there is everything is in the vector multiplier.
Yeah, okay. All right.
Okay. Okay, so the thing is like, so if you imagine you quantize this theory in this bucket, okay? So what you will get, and this is what there. So all these fields are in the joint, right? So you need to multiply them by for SUN. SUN.
But Andres, sorry, I'm a bit confused because n equals 4, you should have 4 fermions, no?
Yes, 4 byte fermions.
Yes.
And each byte fermion has 2 degrees of freedom.
Yes. I count the degrees of freedom, not the number of fields.
Yes.
Okay. All right. Okay. Thank you.
So this is 6 scalar times because all the in the joint.
Yes.
This is multiplied by n squared minus 1.
All right.
Because it's in the joint representation.
Sure.
This also is multiplied by n squared minus 1 times n squared minus 1. For this. Okay? And now let's compute the energy for this, taking the free limit and blah blah. So the thing is like, you will get something like the factor, this numerical factor. Let's say minus p squared divided by 6 delta cube b2x times n squared minus 1, because now I want to multiply by the degrees of freedoms. And I will just add them. Okay? So I have 6 scalars. So let's suppose that I said that they are all periodic.
Sorry, so just something not to be confused. This n is not the same n as it's not the same n as this one, because you have n equals 4 supersedes, but you have some gauge group with SUM, for example.
Yeah, no, this n is the n of SUN.
Yeah, but it's not SU4 that we're talking about.
No, this is
calligraphic.
Okay.
Yeah.
All right.
Yeah.
Okay.
Yeah, this is the problem with physicists, you know. They use n for everything. There is also n here. To the sun. I used to have a physics student that called all the Greek letters mu. Because it was messy. So then you just need to add say this is the value, the potential value of supergenius. Okay? So here you have to add this guy. So you just have 6 plus 2 minus 8. And you get the max. So when you quantize all of them with the same boundary condition, because this guy has the negative sign, that you get this already. You remember when you quantize the fermion, just in Minkowski, and you do this normal ordering, you get that you get a minus delta 0 for the fermion and a plus delta 0 for the boson. And so here is the same, right? So here you get this is 0. So this kind, like if you quantize all of them with the same boundary condition, you preserve supersymmetry, and then it is 0. Okay. So this is preserved supersymmetry, and in a sense, This is necessary, right? Because if you are going to transform bosons and fermions and bosons, they need to have the same boundary conditions, otherwise it doesn't make sense, right? Well, you cannot transform something periodic into something antiperiodic. At least 90 million, right? Now, actually, if you do this calculation for with different boundary conditions and you break supersymmetry, so imagine.
But sorry, I didn't understand one point. You said that if you have for instance, a scalar, you have 8 over 120 if it's periodic boundary conditions, and -7 if it's anti-periodic, and you said that you changed the whole.
No, I said it wrongly. It's like you change the sign.
Okay.
You get the same numbers,
perfect.
but with different sign.
Okay, perfect.
This is the correct step. Okay, so same. So imagine now you quantize this like with periodic, this with periodic, and the other you quantize with antiperiodic. Okay, so you see this periodic is plus, well, because there is a minus. So minus, so periodic is plus. Antiperiodic, sorry, periodic is plus, periodic is plus. So antiperiodic, you should get a minus here, right? 7 or 8. It's because like you get a plus.
This is the Fermi contribution quantizing the anti-periodic.
Yeah, it's a plus.
Okay.
So this is this. Because you make this periodic, and this is
so it's 8 times
antiperiodic times 8. Okay?
Okay.
Because here you put everything periodic. Because of the numbers, one is 7 over 8, the other, right? So you just get the periodic factor times a 7 over 8, you get the antiperiodic, but with the other sign, because it's Fermi. And this is the result. Okay? And then, so you just need to add them up. And so you get 6 plus 2 is 8, plus 7 is 15. Right? So 15 times 8 is 120, which cancels this 120. Okay? So this is just this experiment cancel, right? Experiment cancel with this 15,
Okay.
and then we get minus pi squared divided 6 delta cube b2 n squared. I think this is the result. Okay, very good. Now we will do this calculation using gravity. Okay?
And if you don't have any residual supersymmetry, you break all the four supersymmetries.
Yeah, here you break it.
Completely.
Completely.
Okay.
So this is the background expectation value of the Hamiltonian of the free field theory using just the free field theory of any part for superunits. And this is the result. Okay? And I will do this calculation using gravity now. So to use this, so you see, like I need to somehow tell my gravity theory that I have antiperiodic fermions. How I do that? And this is like, you know, everybody studied this, but nobody paid too much attention. But so actually, I just remember it. Like, you know, like when you have like a fermion, like for instance in this bar, like just plain planar, and you want to like you construct this fermion, you need to use the field line, right? To construct fermions, you need the field line formalism, and you will, if you do this for the polar coordinate, you get that the fermion will be like whatever you choose, 1, 0. e to the I phi over 2. Right? Because this phi is contractible. So this is the thing. So this is like when you have a cycle that is contractible, the fermion must be antiperiodic. This is like because like when you go back, like if you write this, because you can write this in Cartesian coordinates. You know it's the same. When you go back to Cartesian coordinates, if the fermion is not antiperiodic, it's not regular. You get something like a strange representation that is not regular. So it has to be antiperiodic to be regular, right? So and so people say that this, like the mathematicians say, is that when the cycle is contractible, like in this case, there is only one spin structure. If it's not contractible, then there are two spin structures. One, when it's not contractible, you can choose either periodic or antiperiodic boundary conditions. That is the two ways, for instance, you can type fermionic string. No? Then there are two boundary conditions, the Ramon, the neighbor shots, because the cycle of the string is not contractible. It's a cycle. So here it is contractible and then it's only one. So fermions have to be antiperiodic always when you have a contractible cycle. In this cycle, they have to be antiperiodic. So a way to impose this condition of antiperiodicity here, and therefore going back to the beginning of the talk, so a way to impose that I am using this Hilbert space with antiperiodic fermions in the gravity theory is to have a theory where this cycle is contractible in the bank, in the radial direction. And then all the fermions have to be antiperiodic automatically. So then you select, in this way you select a state in the QFT using a geometrical condition in gravity. You see? Very beautiful. So what I need, is something contractible. And there is a very simple method that has this property, that is this. R square over L square minus mu divided by R square. Okay? And this is called the AES solid. This metric is kind of famous. And this idea that I am telling you was originally proposed by Horowitz and Miles, okay, in the 1980s. So, of course, when you see, like, there is an R plus that is 0. So, that is when mu is equal to, so you say that mu is equal to R plus to the 4, right? So, automatically when R is equal to R plus, F is 0, right? So then the cycle is contractible, and then all fermions, but then the theory has the information. You give the information to the theory that you're working with antiperiodic fermions, because the cycle is contractible. So this is the map between geometry and the Hilbert space that I was talking about. Okay? So now let's compute the energy here, and see if we get this number. So we need to. So the first thing is, like, of course, if we are going to transform our information from the gravity theory to like a QFT, we need to get rid of everything that is not geometrical, right? Because mu is whatever, right? Mu is something that I invented today, call it mu. Right? This can be 2 mu, 3 mu, so it doesn't mean nothing. Mu is nothing. And L, of course, there is no L in the in the QFT, there is no L, so I need to get rid of all this. And the way to get rid of all these things is to rewrite everything in geometrical terms. And then everything disappears. And this is very cool. So what is geometrical is the cycle of phi, right? Phi goes between 0 and delta.
So you are saying that you are going to redefine your geometric objects by introducing these factors.
What I'm saying is that I will write mu in terms of delta. Because delta is geometrical, has a geometrical meaning. That is the size of the set, right? Mu has no meaning, no invariant meaning, right? This is the set. So then, like delta to the -1 is defined as f prime in R plus divided by 4 pi. That is similar to the formula of the temperature, right? Because this is what makes the cycle regular. This is the condition of regularity. Then you get rid of conical singularities, and this is the condition. So I need to compute this. So f prime is 2r plus divided by L squared plus 2 mu divided by R plus Q, right? This is the derivative with respect to R. This. And now I replace mu is R plus to the 4 here. So I get that this is plus, so this is equal to 4 R plus to the 4 divided by H. So this is delta. And no, it's 4 R plus. Because mu is R plus to the 4. Divided by R plus Q is R plus. So you get 2 times the same. So then I can say that R plus is equal to L squared divided by 4 delta. Right? 4 pi.
There's a 4 pi overall. One over.
Yeah, here
Yeah.
I miss a 4 pi. 1 over 4. So this 4 cancels, you get pi. So R plus is equal to pi L squared. Good. I would have a problem with pi, like all physicists, you know. It's a problem. We have always have a problem with pi or with square root of 2. What is the square root of 2? So this is the condition that give me an invariant definition of R plus and also of mu, right? So now you can compute the density of energy of the solution using your favorite method. There are infinite methods to compute the density of energy for a gravitational solution, right? And you will get this. You will get, of course, it's proportional to mu, right? Because mu is the energy, it's like the Coulomb potential, right? In 5 dimensions. And then you get that this is minus mu divided by 2 L8 pi G. This is the error. So now you use that mu is this guy here, and then that R plus is this, and then you can write this in terms of delta, which is the importance, right? So this is now minus pi. delta 2. And you have to use, there is something called the ADS-CFT dictionary, who tell you, like these two guys in 5 dimensions, so G Newton in 5 dimensions, this is equal to 2n squared divided by where n is the n of SUN superunits.
Oh, Andres, so in this case you are computing for formulas which are coupled to gravity.
Well, no, this is the magic. Here I compute the energy of the gravitational solution.
Okay.
Of the gravitational, like when you compute the energy of the black hole.
Okay.
Right? You go and you have this is a solution of the Einstein equations. Okay? And then
But without matter.
Without matter.
Okay.
So this is like this solution of the Einstein equations have inside the energy of the QFT. So this is what I'm trying to show, right? Without Fermi, so here there is no Fermi, here there is no boson. It's like you just put the in your your input is that you want a contractible cycle. And this contractible cycle select the Hilbert space of the QFT. You see? Because when you have a contractible cycle, you get antiperiodic fermions, for sure. Right? And then you get this calculation that I did. Right?
The L is what? It's a
ADS radius. L is the ADS radius. The ADS radius.
okay.
So the Einstein equations, so this things satisfy these equations. Minus 1 over 12. And so G. These are the Einstein equations in 5 dimensions. Okay? So L is the ADS radius, but is rated with the cosmological constant known as E times the minus 1. Okay. So and so yes, so you see like G Newton has units of length squared in natural units, no? Where h bar is equal to c is equal to 1. G has units of length squared, right? In 4 dimensions. And because the Coulomb potential goes like 1 over r squared in 5 dimensions, G has units of length cube now, right? So this is dimensions. So the ADS radius divided by G Newton in 5 dimensions. And this is by the duality. This is the match that people use for all the holography. So you don't change this for every calculation. So this is universal. This is a universal thing that you always use to don't cheat with yourself, right? So you always use these numbers. Okay. And this is what maps allow you to rewrite your gravity calculations as QFT calculation, because you can get rid of G Newton. Of course, if you have a gravity calculation, everything will have G Newton, and everything will have ADS radius. What I'm trying to say here is like, look, when you write this thing in terms of a geometrical object, that is the period of the cycle, you always get this factor that now you can rewrite as in terms of L, right? So this is, this is just a 2, so this is minus pi cubed divided by 8 G, no, G, no, this is not G, pi squared, right? Pi squared, the 16 cancel, the pi cancel, n squared, delta 2. Okay? So, well, you get the pi correctly. No, but the thing is like, well, this is the energy density, okay? And this is the energy. So I need to multiply the energy density by the volume, or divide this by the volume of the 3 space, right? So if you divide E by the volume of the QFT, where the QFT lives, which is B2, where B2 is this guy, is this volume of this. The volume of this is B2. And you also have this phi, which is like the energy of superjump means divided by V2 divided by delta. You will get rid of this V2 and you will get a delta in the denominator. So you get minus pi squared divided by 6 delta to the 4 n squared minus. Okay? So would you see that so this is the equal, this is equal the energy density of the superjump missile is function of the Tosca. So when lambda goes to infinity, well, this is f equal infinity. When lambda goes to infinity, you go to the gravity calculation. And when lambda goes to 0, you go to the superjump. And people have computed this f of 4. People compute this, and they see that this goes in the right direction. So this is a very simple calculation that has a lot of physics, you see? Because you compute the energy in a background, gravity background, and you get the energy of an interacting QFT. It's crazy, you know? And this is why this is so interesting. Huh?
Two things. The first one is that there is the -1 together with the n squared, probably in the relation that you use the L cubed with G. It's 2n squared minus 1, maybe, no?
Well,
match perfectly.
very good, very good. No.
No?
No. No, because like this is supposed to match when n goes to infinity.
Okay.
And this is why people say that gravity is the large n limit of superjump missile. So you need to take n to infinity and lambda to infinity.
Okay.
And in these two limits, you get holographic.
And the second question is, when we did the computation from the quantum field theory side, we said that we were taking the free field approximation. Somehow we didn't consider the interactions. So if you try to consider the interactions, maybe we'll have corrections. And in this limit, this correction is also vanished. The result is also good. It's also you still have the match.
Well, like what I know is that people know how to compute, like still in the large limit, but to compute finite top corrections, and people have done that. And in that case, that have the right without large n. But large n is cool because large n still you still have all loops in large n. It's just a group of all loops, right? It's the group that are planar. So you don't get the non-planar diagrams, but you still have all quantum corrections and all. So this kind of calculations make you think that this is kind of fundamental, right? That this is kind of a new way of looking at QFT. Like doing a completely different calculation, which is what physicists love, right? Because it's like now you see in this, because this is just mathematics, right? But what makes it like beautiful is that what you say about this mathematics, right? And this mathematics now you say this is a QFT, right? Well, before you never thought about it, and this is cool.
No.
If you have some, if you somehow brings n equals 4 supersymmetry to n equals 2, and you have some n equals 2 supersymmetry, can you have some sort of analog of?
Yeah. This have been done. This have been done and have been studied a lot because people actually have the crazy hope that they can describe realistic things. Because of course, okay, this is cool, but all is very supersymmetric and you need a lot of assumptions. And when you put all these assumptions, then it's super cool. But when you start removing assumptions, it's a mess, you know. But people have done a lot of progress actually, and there is a whole program that people call it holographic QCD, where they have hopes. Other people think that this can never work, but but anyway, what do you know? Like, some people I hear before they mention gravitational waves. I hear very respectable people who say this will never work.
Well, people went to FNJ and they work with holographic QCD, so I hope that. Oh, I have one curiosity more. You said that when you choose the cycle to be non-contractible or contractible, then you impose that necessarily the fermion must be quantized with untyped
Yes, yes.
But in the other side, we could choose.
Yeah,
the result would be the same.
Yes.
And here you cannot choose.
You cannot choose.
Okay.
So this is why I say that this pick a Hilbert space in the QFT.
Okay.
This solution pick a Hilbert space, a very precise Hilbert space. You are not in the other Hilbert space where the fermion is periodic. You are here in the Hilbert space where the fermion is antiperiodic. So this solution somehow have all this information, have the Hilbert space of the QFT in that case. And for the other solution, you need another, for the other Hilbert space, you need another solution, right? Where the cycle is not contracted.
Thanks.
So, Andre, do you think that the fact that any post-force superimposed is finite, perturbative and finite, it has to do something with this fact that you have this sort of equivalence to photography? I ask if the ultraviolet behavior of the theory would have something to do with this result, or it's just
as I understand, like what people, how people think about this is that they know that string theory is in a limit anywhere for supergravity, and they know that in another limit is supergravity. So then they say, well, actually this is not only in the limit, but it's like these two descriptions match order by order when you do this expansion.
Maybe, I don't know. If you want to have a conformal symmetry even at the quantum level, I think it must be superimposed n equal to 4. No, I think at n equal to 2, you could have a non-zero beta function.
Depends on the gauge group.
Depends on the gauge group.
Depends on the gauge group and
So you can choose the gauge group. Okay.
You have to match two things, the gauge group and that gauge group you have to see how to put the representations to kill the data function.
I see. So it's possible with n equal to 2. Oh, okay.
So here, the thing is like what people have done is like, for instance, here, you know, like the fermions in the standard model fermions, they are not in that joint, they are in the fundamental, right? So what people have worked is that he said, okay, how I represent the fact that fermions are in the fundamental in the gravity cell. So how I capture this, and people have made a lot of progress. So, or how I represent that I have, for instance, n equal 1. So n equal 1 supergenerals with fermions in the fundamental is really n equal 1 QCD, right? And then people with that they have made a lot of progress, and I think that is quite okay. So actually, something you can do with this that is very interesting is that you can study phase transitions in the gravity cell, like the copy paste phase transition. Right?
It's interesting because we were discussing this like 2 days ago. A guy that's working in the Wi-Fi Jota group is working exactly with this. He's looking from the idea safety perspective, like hooking page positions and the rotation, the effect of rotation in this kind of systems in QCD using the holography. So
yeah, but actually I published a physical regulators with that last year, and
nice.
it's really something new that is going on.
yeah.
So and this is like, imagine I tell you, okay, can you compute the partition function of QCD at finite temperature and finite chemical potential? No, of course not. Nobody can, right? And with chemical potential, you have the sign problem also in it. So because the A nu is real, when you go to the lattice, you need to do a Euclidean lattice, right? And then A nu becomes imaginary, right? Because it's real. So when you do the weak rotation, the chemical potential becomes imaginary, and this is very problematic for the lattice. And here you can do this computation like in one page. You just I compute the energy, I compute this, I compute that, and then you have this. So that's a very promising, I think, idea to compute like at least a sector of the phase diagram of QCD. You can kind of describe using this. Because there is a sector of QCD where the speed of sound is 1 over the square root of 3. So it's almost conformal. So I think that's kind of compromising. Okay. So what time is? How much time?
Probably perhaps 10 more minutes.
Okay. All this was the introduction.
Okay.
Because this is like when you do these technical seminars, you start always from very advanced point and nobody understands nothing. It's like
no, you also use the blackboard. It was good.
So I think with this at least, because at least when I didn't work on these things, all this looked so exotic, so strange. You see, this is American, what is it? Like, it's so strange. And it's not, it's actually, it goes, it's not so strange. Well, then I can make like what I did. So what I did is like, actually, if you think about this really looks like a block. This soliton looks like a block because F, 1 over F, right? A kind of like a metric for the block. So actually this can be done, can be seen like a double with rotation. We call this set. Another we call this time. And this with a minus of the block. It's a double with rotation of the block. For the time is now Euclidean. And one of these coordinates we call it time, and now it becomes a soliton. So the soliton is a double grid rotation of the block. So I did the same, but with another block. But it was super cool because it has a different physics. And it's rising in the node. So it rises in the node. So now you have Einstein equations. So you go to 5 dimensions. So you go to 5 dimensions, and like anywhere is supergravity, has a sector that is universal, that is n equal to, where you have Einstein plus Maxwell plus minus plus clear constant that I don't remember. A which F. So this is your reaction. Okay? So you have n equal to supergravity in 5 dimensions is Einstein with the Maxwell term with Chern-Simons. So this you compute this. So this has some Einstein equation, and you put now an A mu. That is delta mu phi of Q divided by R squared. So you put a Coulomb potential, right? But in phi, not in pi. So kind of a Coulomb potential. So then let's go back to the solution. And this is the double grid rotation of rising node. So you have some field that is supported on this direction, right? So then this gets modified with a minus Q squared R2. So now you have a different solution. And this different solution, you have 2 parameters now, like 2 geometrical parameters. One is this, one is delta, like before. And the other is it's a Wilson loop. You can make a Wilson loop of this guy in this 5 direction. And this will give you like a magnetic flux, right? And like very similar, you're familiar with Hawking page. You know Hawking, no?
No. So one time.
Well, I can explain your Hawking page in 5 minutes. It's super, it's not complicated. So, like, let's do the Hawking page. Hawking page, let's take F. So, let's say you have a black. This black hole has this F. This is in 4 dimensions, okay? That's one. And now we will do the same procedure. So first, so look, f of r plus equals 0 allow me to solve mu. So mu is equal to minus 1, no, is equal to r cubed divided by l squared plus r, right? So r plus, right? Now, second, I do, say beta, or, you know, beta minus 1 is the temperature, right? So beta is the Euclidean period, and the inverse of the Euclidean period is the temperature. And this is equal to f prime divided by 4 pi. Now, f prime is equal to 2r plus, this is r plus, 2r plus divided by l squared plus mu divided by r cubed, right? Plus. And mu is this, so mu, this is 2r plus divided by l squared plus r plus divided by l squared plus 1 over r plus, right? This is correct? And divide by 4 pi. So divide by 4. Right? So f plus f prime, you get 2, and then you get r plus squared, and then you get this seems to be. So then you get the following. Let me define a reduced temperature. Let me define a reduced temperature that is tau. Okay, tau is 4 pi temperature. So I will pass this multiply. And I will get the following. Look, I will get a quadratic equation for r plus. So I get r plus squared divided by, sorry, we got 3, right? So it's 3r plus squared divided by l squared plus 1 minus tau r plus equals 0, right? So this equation I can rewrite it like this, okay? And this has all the physics of continuous. Look, because now I can, this is a quadratic equation. So r plus minus is equal to tau plus minus square root of tau squared minus 4 minus 12 l squared. One half divided by 2 divided by 6, and l squared. Right? So it's the quadratic equation. This is the solution of the quadratic equation. And look what happened. This is telling you that for each temperature, there are 2 r plus. So immediately you learn this. For each temperature, there are 2 r plus. So there are 2 black holes for every temperature in IDs. And there is a minimum temperature. Because if you decrease the temperature too much, this becomes imaginary and there is no r plus. There is no real r plus that satisfies this equation. So there is a minimum temperature. There are 2 black holes. And this is computation. Right? So now you need to do a little bit more. You need to compute the free energy and plot versus tau. Okay? So you will get that the small black holes are unstable. You will get this from this, so you get a cube like this, you know, and the large black holes are stable, and you get another cube like this. Okay, so this is small black holes. These are small. These are large. And there is a point, and this is the minimum tau, right? There is a tau min when there is no more black holes. And so you see, like what people say that happen in ADS is that when you are at zero temperature and you heat the space a little bit, you don't get a black hole immediately. You need to heat more and more and more and more and more and more, and then there is a black hole that forms. And then, but this is like a quantum black hole. It doesn't form by collapse, right? There is not a star collapsing. It's just hot enough space. And then it forms this because this is unstable, so this doesn't really exist. Right? It doesn't exist. Thermal states that are unstable don't exist. You just put particles. So, and then you have this black hole with this free energy. However, this black hole has larger free energy than zero. And there is a specs who have zero free energy, which is ADS itself. So ADS has zero free energy. So here, ADS dominates over the black hole until you reach this point where the free energy of ADS coincides with the free energy of the black hole, and then there is a phase transition. And this is the Hawking phase transition. Okay? And then after this point, the black hole dominates. So this is the Hawking phase in 5 minutes. And so you see, this is the form of the diagram. Like, here you get something similar, okay? Like you complete the energy versus this phi, because here you don't have a temperature, right? So, but you have another parameter. You have an intensity parameter, and then you get something like this. Okay? So you get two branches. You get two branches of solutions for each value of phi, which is this guy, this Wilson group. And you get a supersymmetric solution here where the energy is zero. So there is, because the energy of the, because of the Casimir effect, the Casimir effect has negative energy density. So this soliton has always, there's the one that we computed before. The one that we computed before was this point. So at zero flux. Now we give flux. We give this magnetic flux. And then the energy of this guy, when you start increasing phi, there is a point in which is zero. And this is a supersymmetric solution. It's amazing. And then there is this other guy who, when the flux goes to zero, that solution goes to ADS4. And ADS4 has zero energy. You see? So this solution goes to ADS4, and this goes to the soliton Horowitz and minus. And the fact that this guy is supersymmetric, how come this supersymmetric has different boundary conditions, the fermions and the bosons, and I said this is not possible. And then, what happened is that in the field theory, the fermions are kind of dressed with a source, right? Because when you put a gauge field, you introduce a source in the field theory. So this source give a phase to the fermions that make them periodic at that point.
Actually, this is important. I mean, is there any role of this Chern-Simons term for that?
No, because this is, you need to see, because this, to be non-trivial, you need to have all the legs, because it's a p-form.
Yes.
So you need to have a very complicated, actually, gauge field to have a role, to have this to play a role. This is just a solution of Einstein matrix.
I see. Without Chern-Simons?
Without Chern-Simons. Because Chern-Simons vanishes on this background. So it is a solution with Chern-Simons, but it's zero. So it is a solution of supergravity, of anyway supergravity. So it's a solution of 10-dimensional supergravity. And so these solutions kind of after we published this with Simon Ross, this guy with flux. And after we published this, people got very interested in this, and they studied, because these solutions are also related with confinement. And so people start studying that, and because it's supersymmetric, you can make calculations that you can match with the field theory, and it's very interesting. So this is this paper. And I think you are already tired, so it's better that I finish.
And before we finish, just I had a question. When you get there, that supersymmetric solution, you say that it's 10-dimensional supergravity?
No, but so this solution is 5-dimensional, right?
Okay.
But but this solution, so this Lagrangian is a consistent location of 10-dimensional supergravity. It's ADS 5 versus 5.
Okay.
So and then you can uplift the solution because
okay.
there are the formulas.
Okay. So if you lift the solution,
then you get a 10-dimensional solution, and this 10-dimensional solution is
and you think that would it there be some mechanism, some sort of condensation mechanism of the Fermions of the supersymmetry of the fermionic sector of the supersymmetry? Would happen some sort of this mechanism of thermal condensation?
Well, I like the thing is like there is a way to add fermion condensates, but in the field theory to this.
I see.
There is a way to do this because, like, in this guy, this inequalized supergravity has 42 scalars. So there is 2 who is the dilaton and the axion, the string theory dilaton and the axion. There are 20 who are like they have n squared minus 3, and there are 20 who have n squared minus 4. These 20 are dual to bilinears, to expectation values of bilinears of scalars in n equal 4 supersymmetries. And these guys with m squared equal minus 3, they are duals to bilinears of fermions, to non-trivial pairs of bilinears of fermions. So if you could take this solution, add a scalar field, that is, this is like these are kind of axioms. Okay? You add this scalar field, and you will get a solution who will represent a condensate in the a fermion condensate.
Okay, and this fermion condensate could break supersymmetry. This is what the reason of my question, because I thought that maybe there is some mechanism that fermions can condensate, and by the condensation of gauges, for example, can break supersymmetry. This is why I was asking this question.
Well, I don't know, but because I just studied this case.
I see.
With m squared equal minus 4. Yes. Okay. And in that case, you also find that the solution can be either supersymmetric or not.
Okay.
So we always find this point. So let's say there is this point where the energy is 0. This is like the expectation value of the diminutive is 0. So it's like it's a vacuum. So in that sense, it is this always happens. So I don't know, but I don't know.
Okay, no, thank you. It's just a curiosity.
But it's something that one can explore.
It was just a curiosity because sometimes we consider gauging condensation to break supersymmetry. Since you have this mechanism of 10-dimensional supergravity truncated into 5-dimension, I thought that somehow the gauges could condensate by virtue of the Chern-Simons and the supersymmetry could be broken this way.
Well, I am studying these things now, so if you want, we can look at this. It's a good question.
Okay, so is there any? So thank you so much indeed for your visit, for saying that.
Well, thank you.
Thank you so much.
Thank you for listening. At the end, physics is a social activity, right? You cannot do physics alone.
No, never.
So thank you for listening.
So next year, if you are